Hi everyone, hope you're all okay. This video is going to go through the questions in the distance, speed and acceleration past paper questions booklet. Just bear in mind that if a question in this past paper booklet asks you to use the equations on page 2, it's referring to the formula sheet that you get in the front of your exam, and just so that you're just as a reminder, the equations that you get in that formula sheet are that are related to this unit are speed equals distance over time, and that's given as a word equation and not as symbols on page 2 of your exam. And also acceleration or deceleration, because they're both interchangeable for this unit. Acceleration is the change in speed. Change in speed or the change in velocity over time. And in symbols, we use A is delta V over T. A meaning acceleration or deceleration, delta V meaning change in speed, delta of course meaning change, and T meaning time. On page 2 you also have a couple of other statements, one of them being that the gradient of a speed time graph gives you the acceleration, and that the area under a speed time graph gives you the distance travelled by an object. So just bear that in mind as we work through these questions, that if a question does ask you to use an equation on page 2, it's referring to one of those. So it might be useful if you have your notes open and have that equation sheet in front of you. So question 1 then. This first set of questions is dealing with motion questions, so just general questions from this unit. Pause the video here, have a go at the question, and when you're ready, press play, and we'll go through the answer. So it's easier if we deal with the straightforward ones first. Distance, we know, well, we measure that in meters. Time, measure in seconds. Speed then, mean speed, we use the same units for both. One just means average. Mean speed, we use meters per second. And deceleration, we use meters per second squared. Bear in mind that that unit is also the unit for acceleration, as deceleration and acceleration are interchangeable to a degree with this unit. Pause the video here and have a go at the next question. Okay, so the next question is dealing with a graph showing how the speed of a Formula 1 car changes during the first 4 seconds of a race. Write down an equation as it appears on page 2 and use it to calculate the acceleration of the car. So this part of the graph is where the car is accelerating, that first 2.5 seconds. And to calculate the acceleration, we're going to use the equation acceleration is change in velocity over time. And you could use either the word format or the symbol format for that. Calculation then, well, we want to put in our numbers, but first let's just establish what's what. Delta V, the change in velocity or change in speed, is 80, because we start at 0 and we end up at 80. So change in speed is 80. And our time period for this part of the journey, for the accelerating part of the journey, is 2.5. We start at 0, it takes 2.5 seconds. So the calculation then is 80 over 2.5, which is 32 meters per second squared. So we'll put our answer in the box there, 32 meters per second squared. Moving on then to part B. The average speed of the car is 42.5 meters per second for the part of the race shown. Use the equation distance equals average speed times time to calculate the distance travelled by the car. So let's put in some values. Our average speed is 42.5. The time taken for this journey is 4 seconds. Okay, because we go up there, and down, and then across. So the whole journey takes 4 seconds, And so that is the time that we're going to use in this equation. Okay, because this question is dealing with the part of the race shown. 42.5 times 4 gives 170 meters as our distance traveled. Pause the video again and have a go at the next question. Okay, so the first thing we want to do with this question is just interpret what this diagram is telling us. We're told below it that the diagram shows the positions of the ball at 0.5 second intervals as it rolls down a 10-meter track. So what we're saying there is between A and B, we have 0.5 seconds. Between B and C, again, we have 0.5 seconds. C and D, 0.5 seconds. And D and E, we've got 0.5 seconds. Write down the distance travelled by the ball from A to E. We started at A, ended up at E, which is one short of 10 meters, so that's 9 meters. Write down the time taken for the ball to travel from A to E then. Well, we've got 4 0.5 second intervals. So 4 times 0.5 is 2. And even though that's just a 1-mark question, it's always a good idea to write down your working for any question like that. Part B, use the equation speed equals distance over time to calculate the mean speed as the ball rolled from A to E. Well, our distance we've already established is 9 meters, and the time it's taken us to do that, well, the time it's taken the ball is 2 seconds. 9 divided by 2 is 4.5 meters per second. State how the diagram shows that the ball is accelerating as it moves. So we want to pick out on something that's specifically seen in the diagram, some property of this diagram that shows us that the ball is accelerating. So what we want to say is that the ball travels a greater distance in the same time interval. As the journey progresses. That's the kind of thing we're looking for there. Describe how the positions of the ball would be different if the track were less steep. Well, if we've got a track like that as opposed to one like that, the ball is going to be accelerating at a lower rate. It's going to be accelerating at a decreased rate, which means that to use the wording in the question, which is always a good idea, use the words and the phrases that they give you in the question, the positions of the ball would be closer together. The positions of the ball would be closer together. We could give some explanation then, but it's only 1 mark. We could say something like, because the ball is accelerating at a decreased rate. It's only 1 mark, so that'll do. Okay. This next series of questions is dealing with distance time graphs. So again, stop the video here and then have a go at this first question. Okay, so we've got a distance time graph showing a journey made by a cyclist. Before we look at the question, let's try and interpret what's going on. We've got, in the first section here, the cyclist traveling a distance of 40 meters, and he or she does that in 50 seconds. Then the cyclist stops, we're stationary for, well, between 50 seconds and 90 seconds, and then we start moving again. What we notice is that third part of the journey over here, the graph is less steep than it was initially, and that means that the cyclist was traveling less distance in the same time, so traveling at a slower speed. We also know that these speeds are constant speeds because we've got straight lines as opposed to curves like that. How far did the cyclist travel before stopping? Well, stopped at 50 seconds, gone 400 meters. Using the information from the graph and the equation speed equals distance over time, find the speed of the cyclist in the last 50 seconds of the journey. So the last 50 seconds, we start at 90, we end at 140. Starting at 400 meters, finishing at 600. So we know our distance traveled between those is 200. So distance is 600 minus 400, which is 200. And using distance over time, 200 divided by 50 gives us an answer of 4 meters per second. Now, just bear in mind, one thing I want you to be very careful of when you're doing a question like this is how you set your workings out, how you set your maths out. Because what people often will do is they'll try and just work through in one big step, and it actually means that your mathematical working is wrong. What we don't want to see is something like this, where we say, okay, the distance traveled is 600 minus 400, and that's 200. And then speed is distance over time, so 200 over 50 equals 4. What you're telling us, what you're telling the examiner when you're writing something like that, is that you think 600 minus 400 is equal to 4. And obviously that's not the case. Okay, we need to be making sure that every individual step of our working, just to be safe, is on a new line. So 200 divided by 50, 4. Just watch out for that. Explain how we can tell that the cyclist travelled faster during the first 50 seconds than the last 50 seconds of the journey. Well, like we said at the start of this question, the graph is steeper, which means we're travelling a greater distance in the same time interval. So we want to say that the line is steeper, or the gradient is steeper during the first 50 seconds. Now bear in mind, with that answer, I've not just said that the line is steeper, I've specified which part of the race I'm talking about as well, okay? Because this question is asking me about 2 different time intervals. It's asking about the first 50 seconds and the last 50 seconds. So we need to make sure that if whatever answer we give, we specify which of those periods we're talking about. Pause the video here, have a go at the next question. Okay, so we've got 2 cyclists now, A and B, and we want to, well, we've got some work to do in interpreting what this graph is telling us. So we can see that A, the cyclist that A represents, the gradient is steeper, and that means that they're traveling faster. And we can see that because they cover 1,200 meters of distance in less time than B. So let's see what the questions are asking. Use the graph to find how far B was behind A after 100 seconds. Well, there's 100 seconds. Let's have a look where they are. B is there, and A is there. So A has travelled 1,000 meters, B has travelled 800. So the distance between those two, or the difference, sorry, between those two is 200 meters. So the distance then, 200 meters. How long after A did B finish the race? Well, A finished the race 1,200 meters there at 120. B finished the race at halfway between 140 and 160, which of course is 150. And so between 120 and 150, we've got 30 seconds. So there's a 30-second time difference between them. Use the equation speed equals distance over time to find the speed of cyclist B. Well, cyclist B travelled 1,200 meters in a time of 150 seconds, which gives us a speed of 8 meters per second. Okay, again, pause the video here. Have a go at the next question. This one might look familiar. This was part of the notes, but it's always good to have another look at things like this. So the distance time graph shows part of a journey made by a cyclist. We've only got part of the journey there, but we've got data to fill out then for the rest of the journey. Just a point to note, when it comes to plotting points in science, we want X's, not spots. Make a clear X, please, when you're plotting your points. So our first point is at 60 and 200. Next point is at 80 and 200, and then 100 and 200. And then the distance starts to increase again. So at 120, we're up at 400. And forgive me if my points are slightly off. It's hard to follow the graph lines on the laptop. And then we've got 600 meters at 140, which is up there. Now, I know in physics normally we'd say that we want to do lines of best fit or curves, but we do that if we have two variables that we're investigating in an experiment or in theory. If we've just got data for a graph for distance and time, then we just do join the dots. So we'll join those, and you should be doing this with a ruler. And they should have, well, you should have two straight lines there. Use an equation from page 2 to calculate the speed of the cyclist during the first 40 seconds. Well, we're going to use speed equals distance over time. In the first 40 seconds, the cyclist has travelled 200 meters in 40 seconds. And so 200 over 40 gives us a speed of 5 meters per second. How long was the cyclist not moving then? Well, the cyclist stops at 40 seconds. You start moving again at 100. And the difference between those, is 60 seconds. So 60 seconds there. Now we know that the cyclist isn't moving for this part of the graph because time's going on, but the distance isn't changing. He's staying at 200 meters, which means he's not moving. Okay, this next set of questions goes on to talk about speed time graphs. Pause the video here and have a go at these. Okay, key point to note when it comes to interpreting what this question is saying. The graph shows how the speed of an athlete changes after crossing the finishing line of a race. So this whole graph is dealing with after the athletes cross the finish line. What was his speed when he finished the race? Well, at time 0, which is when he crosses the finish line, speed is 10. So 10. But notice that with this question, we haven't been given units. So we have to make sure that we add our units to this answer. In all the previous ones, we've been given the units next to the line that we put our answer on. And if you're not sure of what the units are for your speed or your time or whatever, just check the graph. Time is in seconds there. Speed is in meters per second. So speed when you finished the race was 10 meters per second. At what time is the speed equal to 2 meters per second? So looking at that speed now. Well, we need to work across and then down, and we find that the speed is, the time at which his speed is 2 meters is 3.5. And again, we need to put a unit with that, seconds. Using the equation then, deceleration is change in speed over time. Let's calculate the deceleration in the first 2 seconds after finishing the race. So in the first 2 seconds, we're dealing with this part of the race. That's the first 2 seconds. Our change in speed here, we go from 10 to 4. So the change in speed is 6, and the time period is, well, 2 seconds. That's what they've asked us to investigate in the question. So delta V, we said, was 10 minus 4. Remember, we want a new line now. We can't just start dividing by 2 there. We've got to make a new line to show that, well, to have our correct maths. 6 over 2 is 3 meters per second squared. But they've given us the unit there, so we won't put that on that line. How does the graph show that the athlete's deceleration between 2 and 5 seconds is lower than that calculated in C1? Well, we need to remember here that for a speed time graph, speed time graph, our acceleration is shown by the gradient of the graph. And the second part of that race, from 2 seconds to 5 seconds, which is this bit, it's less steep than our first part. So we would say that the gradient is less steep. Again, we want to say which part of the journey we're talking about when we give that answer. The gradient is less steep between 2 and 5 seconds. Moving on then, pause the video and have a go at this one. Okay, so the graph shows part of the journey of a car. Again, let's just interpret this before we have a look at reading any questions. Our speed here doesn't change for the first 10 seconds. We've got a constant speed. Then we're accelerating. Then we've got a constant speed again, and then a deceleration. So that's what we've got going on here. What's the starting speed of the car? 2 is where we start off. Again, we need to give a unit with that, 2 meters per second. What's the maximum speed of the car? Well, the graph takes us up to 8 meters per second. And then how long was the car speeding up? Well, we start accelerating at 10. We finish accelerating at 40. And so our time period for the acceleration is 30 seconds. 40 minus 10. Again, we need to make sure we've got a unit with that answer. Next question then. Again, pause the video and press play again when you're ready. So the graph shows the first 20 seconds of the motion of a van already moving at a constant speed. So the van, like we can see there, is moving at 20 meters per second, and it does so for the first 20 seconds of our journey here. At 20 seconds, the driving force is increased, so the driver puts the foot down, and the van accelerates for 20 seconds to reach a new constant speed of 30 meters per second, which it then continues with for another 20 seconds. Complete the graph to show the motion of the van between 20 and 60 seconds. So we're going to start by just plotting this point, okay? 30 meters per second. We hit that 20 seconds after the acceleration starts. So we're going to be there. We're going to bring our line up like that. And then we were told that the van continues at this new constant speed for a further 20 seconds. And so for the remainder of the journey, we're staying at 30 meters per second. So your graph should look like that. Write down an equation from page 2 and use it to calculate the average acceleration of the van during the period of when it's accelerating. The equation that we're going to use is A equals delta V over T. Acceleration is change in speed over time. Our change in speed here, we've gone from 20 to 30, so the change is 10. The time period is 20 seconds. Again, going back to the graph, we've gone from 20 to 40, so 20 seconds there. And so delta V over T, 10 over 20 is 0.5. We've been given the units there. Diagram shows the horizontal forces acting on the van. Okay, so we've got driving force pulling it forward, drag force pulling it back, and we know that the van is moving forwards. Driving force is 1,000 newtons between 0 and 20 seconds. The mass of the van is 2,400 kilos. Between 0 and 20 seconds, the drag force is also 1,000 newtons. Explain why this must be the case. Well, let's remind ourselves what's happening between 0 and 20 seconds. Between 0 and 20 seconds, we are moving at a constant speed. And so this question is one that's bringing in Newton's laws. And sometimes we do get crossover between distance, speed, and acceleration questions and Newton's laws. So Newton's first law tells us that a body will remain in a state of uniform motion, or in other words, a body will either remain at rest or it will keep traveling at a constant speed unless there's an external resultant force acting on it. So let's check, is there a resultant force acting on it? Sigma F here is 1,000 minus 1,000, which is 0. So no, there's no resultant force, which means the object is going to remain traveling at a constant speed. So explain clearly why this must be the case. Why is the drag force also 1,000 newtons? So what we're going to say, the van is traveling at a constant speed. It's traveling at a constant speed between 0 and 20 seconds. For this to be the case, there must be no resultant force. And so the drag force must be equal to the driving force. That's the kind of thing we're looking for there. Use the equation then, resultant force equals mass times acceleration, to calculate the average resultant force in the van between 20 and 40 seconds. Okay, well, the mass we've been given earlier is 2,400 kilos. We already calculated the acceleration between 20 and 40. We did that on the previous page. And that value is 0.5 meters per second squared. And so the resultant force, MA, equals 2,400 times 0.5, which is 1,200 newtons. So that's our answer to part 2, 1,200 newtons. Part D then, on the grid below, sketch a graph to show how the resultant force in the van changes between 0 and 60 seconds. Well, we've already established for the first 20 seconds, if the van is traveling at a constant speed, there's going to be no resultant force acting. And we also saw on the previous graph that between 40 and 60 seconds, the van is traveling at a higher constant speed, but still a constant speed. And so the force there, the resultant force rather, is going to be 0. Now I am shading these in a little bit more so you can see it clearly, but you should just have one straight, clear line, okay? Between 20 and 40 though, we've calculated what the resultant force is. It's 1,200, which is there. And then we'll just link these up like that. So that's what we should have for the resultant force changing over time. All right, pause the video here. Have a go at question 4 from the speed time graphs. Okay, so this is just a pretty simple 2 marks. A car traveling at a speed of 12 meters per second crashed into a wall and took 0.12 seconds to come to a stop. Use the equation deceleration equals change in speed over time to calculate the deceleration of the car. Well, it's gone from 12 meters per second to a stop. So the change in speed, 12 to 0, is 12. And then the time period is 0.12. And that gives us a value of 100 for our deceleration. Nice and easy. Okay, have a go at question 5. Press play again on the video when you're ready to check the answers. Okay, part A. Use the graph to find the total time that the train was travelling faster than 5 meters per second. I'm going to draw a line across from 5 meters per second. Oops. And all I want to do is check how much of the motion is over that time period. So our first part there is over 5 meters per second. So between 0 and 20 seconds, that's when we drop below 5. Between 0 and 20, we're above 5 meters per second. And we're also above 5 meters per second over here as well. And so I need to figure out what this point is, where we get higher than 5 meters per second. And that is 85 seconds. Okay, let's just make sure we understand why. 90 is halfway between 80 and 100, and we're halfway between 80 and 90. So 85 is when we go above 5 meters per second for the second time. And we're above 5 meters per second all the way through to 120 seconds. So 120 minus 85, minus 85 is 35 seconds. Okay, so we'll say between 85 and 120. So that gives us 20 seconds, that gives us 35. 20 plus 35 is 55, which is our total time. You need to have that step to win the first mark here. You've got to show this piece of calculation. Okay, it says in the question, show your workings. So we need to have that line. Okay, part B, this is a 6 marker asking us to describe fully the motion of the train. So just to remind you, when we answer 6-mark questions in Go, this is what we do. Every sentence we compose of 3 elements. Firstly, we talk about the time, what times we're dealing with for this particular sentence. Then we say what happens. Say we describe what happens. Is the thing accelerating? Is it decelerating? Is it traveling at a constant speed? Is it not moving? Then, as our third part of the sentence, we give data from the graph, or we give calculations to support what we're saying. So every sentence in this answer is going to be composed of those 3 things. And all I need to do then is split the graph up into different chunks for me to talk about. So I'm going to start off with that little piece at the top. Then we've got that deceleration. Then we've got this stationary bit. And I'm going to split this curve up into 2 parts. I'm going to split it there halfway along the curve. Do this as one part and this as another. And the reason I'm doing that is because for part 4, we can see that the train is accelerating at an increasing rate. The gradient gets steeper and steeper and steeper. But then once we move into part 5, the acceleration then changes to increasing at a decreasing rate. The thing's still accelerating, the speed is still going up, but the amount that it's going up is decreasing every time. The gradient's getting less steeper as we hit the end of part 5. So that's why I've split that into 5 parts. So again, using this structure, this is how I'm going to write my answer. We start with the times. Between 0 and 10 seconds. The train is traveling at a constant speed. So that's me having dealt with the time and what's happening. Now I need data. Pretty simple thing here. What is the constant speed it's traveling at? 10 meters per second from the graph. Sorry, I should say constant speed of 10 meters per second. Okay, that's part one dealt with. We've done the times, what's happening, given data. Part two then, which is our deceleration. Between 10 and 30 seconds, the train is decelerating at a constant rate. It's decelerating at a constant rate. And we can say that by looking at the graph because we've got a straight line. Okay, we've got a straight line going downwards. So that's a deceleration at a constant rate. Let's give some data. We're going from 10 meters per second to rest. And then we're going to do some calculation with a deceleration of, now what I suggest you do for this part is leave a little gap, and then we're going to put some brackets in to do our working, and then we can just go back and fill the gap with the value that we find. The value of A, acceleration, is change in velocity over time. Remember, for that equation, acceleration and deceleration are interchangeable. The change in velocity was 10, going from 10 to rest, so the change is 10. And the time period is 20 seconds, which gives us a value of 0.5 meters per second squared. So I'll go back and fill in the gap that I left with a deceleration of 0.5 meters per second squared. Moving on to part three, between 30 and 60 seconds, the train is stationary. Train is stationary. It's not moving. Now we don't need to give any data to go with that. We know that stationary means speed of 0. Moving on to part four then, between 60 and 90 seconds, so next part of the graph, the train is accelerating at an increasing rate, That means it's going like that. It's that kind of shape for part four. Okay, the train is accelerating at an increasing rate from rest to, let's see what speed we get to in part four. At 90 seconds, we hit 7.5 meters per second over here. 7.5 meters per second. So from rest, 7.5 meters per second. And now we can do another calculation. We can work out what the average acceleration is. Bear in mind, part four now, the acceleration is not constant. We don't have a straight line, but we can work out the average acceleration. We can work out what the average is. So we'll say with an average acceleration of, again, we'll leave a gap there. I'll do the calculation down here this time. I don't think I'll be able to fit it in that gap. A, again, is delta V over t. Our change in speed was 7.5. Time period is 30, and that gives a value of 0.25 meters per second squared. So fill in the gap of 0.25 meters per second squared. And then we've got the final part to look at, which is between 90 and 120 seconds. train is accelerating at a decreasing rate. It's accelerating at a decreasing rate. What that means is it's still accelerating, but the amount it's accelerating is getting less and less over time. That's the kind of shape that we've got. Okay, so accelerating at a decreasing rate from 7.5 meters per second to 15 meters per second. Again, we want to calculate the acceleration with an average acceleration of, let's do the calculation. A is delta V over t. Our change in velocity is 7.5 again here, so we're going from 7.5 to 15. So 7.5 over 30 again, between 90 and 120. That gives us 0.25 like we had before. So they're actually the same average acceleration. So let's put that in here, of 0.25 meters per second squared. And we might think, okay, well, couldn't we have just treated from 60 to 120 seconds as one big chunk, since the average acceleration is the same? And yeah, we could have, but we've gone into a little bit more detail and we've been able to explain that it starts off accelerating at an increasing rate and then it accelerates at a decreasing rate. Okay. Now notice, for each of the sentences I've written here, for each of those 5 sections, I've given a time, said what happens, and then I've given data and a calculation to support what I'm saying if I can. When you write answers to 6-mark questions like this, you are going to be following the exact same structure, or you should be following the exact same structure as I've done there. It'll guarantee you 6 marks if you get the calculations right. Moving on then, use the equation distance equals speed times time to calculate the distance travelled by the train for the first 10 seconds of the journey. It's travelling at 10 meters per second, that's the speed, and it does that for 10 seconds. So nice and easy, 100 meters is our distance there. And between 10 seconds and 30 seconds, the train travels another 100 meters. Use an equation from page 2 to calculate the mean speed of the train between 0 and 60 seconds. Okay, so it's important to note here, they're asking us to calculate the mean speed of the train between that time and that time. We've just worked out that we go 100 meters there, and they've told us that between 10 and 30 seconds, we go another 100 meters. So our total distance are those two, and our total time is that. Now I know you might think, but hold on, we're not moving between 30 and 60 seconds, so why are we including that? Well, we're including that because they've asked us to calculate the average speed between 0 and 60 seconds. So to calculate the average speed, we do the total distance divided by the total time that you're looking at. Our total distance is 200 meters, and our distance over time, 200 over 60, gives us 3.33 meters per second. So our answer to this question, is 3.33 meters per second. Use the graph to estimate with the calculation the distance travelled between 60 seconds and 120 seconds. So we need to think back to page 2 and what you see on page 2 here. Remember that on page 2 you're told to work out the distance travelled on a speed time graph. We can calculate the area under the graph. So distance equals area under the graph. Okay, so we're going to have a look then. What's that going to look like? Sorry, this is playing up a little bit. Okay. So we're looking at between 60 and 120 seconds. We're dealing with that curvy thing. And on the face of it, that's a very difficult thing to work the area out of. Okay, how are we going to calculate the area under here? The question does say estimate. And so what we're going to do is, let's imagine that this is just a triangle, like that. It's just a triangle. I'll try and do that again and get it to go where I want. Oh, almost. No, that's not bad. Okay, so the reason that this estimation works is because we've actually got the same area there that we are adding to our curve as we are taking away under there, if my line was straight, but you get the idea. So really what we're doing is we're working out the area of the triangle there, which has a height of, it has a height of 15 and a base of 60. And then it's just a matter of GCSE maths, remembering that the area of a triangle is half base times the height. Hanner ichter liosi which is half times 15 times 60. I know I've got those the other way around compared to the word equation, but that doesn't matter. And that gives us a value of 450 meters. So that's the distance traveled there. Okay, pause the video here. Have a go at the next question. Okay, so we've got a theme park ride here involving a group of people. They get lifted and then they get dropped. It's in Drayton Manor, so they say. The graph shows the motion for such a ride. Now, this graph seems to be a little bit all over the place, but let's just figure out what's happening. Our first 20 seconds, the speed is down at 5 meters per second, and the vehicle's traveling at a constant speed. It stops then for 10 seconds between 20 and 30. We're stationary. And then we accelerate from 30 to 35 seconds and then decelerate again in 1 second between 35 and 36 seconds. So that's what's going on in that graph. Describe the motion of the carriage in the first 20 seconds. Well, like we said when we were interpreting what's on the graph, the vehicle, we'll use the word in their question, the carriage is traveling at a constant speed. Let's just give them a little bit of detail. Constant speed of 5 meters per second. Use the equation, acceleration is change in speed over time, to find the acceleration of the carriage between 30 and 35 seconds. Okay, well, we've got our time period there, it's 5-second interval. Between 30 and 35, we're accelerating up to 45 meters per second. So our change in speed is 45. Our time is 5 seconds. So meters per second is the unit for our change in speed. And so delta V over T, 45 over 5 is 9. We've got an acceleration of 9 meters per second there. This question's been added in then. How far does the carriage fall? Show your workings. So again, if we want to work out distance, like we saw in the previous question, we need to work out what the area under this triangle is. Okay, and we want to work out the area for the whole 36 seconds there, because although the carriage here is decelerating from 35 to 36 seconds in this little sliver, although it's decelerating, it's still traveling downwards. So again, using our equation for a triangle, our base there, our sile, is 6. The height of the triangle is 45. And so to work out the area, to work out the distance, so the distance is the area under the graph, which is half times 45 times 6, which gives us a value of 135 meters. Okay, pause the video here, have a go at question 7. So the graph below shows a car of mass 1,200 kgs, braking hard to reduce speed before entering a speed restriction area. Use the graph to find the average speed of the car between 30 and 40 seconds. Okay, one way to do this is to just find the halfway point of the graph, which is there, 25. Halfway on a straight line is the average. Another way to think about it is we start off at 40, we end up at 10. 40 plus 10 divided by 2, so the average of both of those is 25 meters per second. The average speed then 25 meters per second. And use the equation distance traveled equals average speed times time to show that the distance traveled is 250. Well, that deceleration takes place over 10 seconds. So our time is 10. Our average speed is 25. So 25 times 10 is 250 meters. So that's the distance traveled during that braking. Pause the video here and have a go at the last question on this video. Okay, so again, we're starting here with a 6 marker asking us to describe the motion of the bus during the 70 seconds that we've got it shown there. So, reminder, how do we set these out? Oh, sorry. We start off every sentence talking about the time. Then we say what happens. Then we use data and calculations to support our answer. We have to split this up into bits. So I'm going to say that part 1 is that constant speed at the start. Part 2 is this acceleration. Part 3 is that constant speed. And then part 4 is this non-constant deceleration. If we think about what shape this is, initially we've got a really steep gradient at B. But over time, that gradient gets less and less steep. So what we have here is deceleration at a decreasing rate. At a deceleration at a decreasing rate. So we're going to construct a sentence for each of those 4 parts of the graph. Firstly then, between 0 and 10 seconds, that's our first section. The bus is traveling at a constant speed of 5 meters per second. Given the times, said what's happening, given the data. Part 2 then, second part, and remember, when we decide to split this up into parts, you've got to make those choices in the exam as to which parts you choose to split it up into. Okay, so you've got to make those choices, and don't just split it up into blocks of 10 seconds. Split it up into sections based on what the vehicle is doing. Okay, so part 2, we're going from 10 to 20 seconds. So between 10 and 20 seconds, bus is accelerating, speed is increasing, bus is accelerating, and it's a straight line from 10 to 20 seconds. Okay, it's not curved, that's a straight line. And so we'll say that it's accelerating at a constant rate. bus is accelerating at a constant rate from, sorry, not from 10 meters per second, from 5 meters per second up to a speed of 20 meters per second. So from 5 meters per second to 20 meters per second with an acceleration of, let's calculate it. We're going to leave a gap there and jump down here. Acceleration is the change in velocity over time. The change in velocity, well, we've gone from 5 to 20, so that change is 15 over a time period of 10. So we've got an acceleration of 1.5 meters per second squared. So to fill in the gap then, 1.5 meters per second squared. Move on to part 3, which is going to be nice and easy. So we've got a constant speed. So between 20 and 40 seconds, let's just check. Yeah, from A to B, we're going from 20 to 40 seconds. So between 20 and 40 seconds, the bus travels at a constant speed of 20 meters per second. The speed the bus is traveling between A and B is 20 meters per second. And then our final section, part 4, between 40 and 70 seconds, the bus is decelerating at a decreasing rate. Okay, remember we explained why, because our graph goes like that. Speed's falling really, really sharply to start with, but then the speed doesn't fall so much later on during the deceleration. So the bus is decelerating at a decreasing rate from 20 meters per second to rest with an average deceleration. Remember, I've got to say average now because it's not constant. So an average deceleration of, let's leave a gap and do our calculation. A is delta V over t. Change in speed here is 20 over a time period of 30. And so our deceleration is 0.67 meters per second squared. Okay, so let's just check. For each section of the graph, we've used time intervals between 0 and 10, between 10 and 20, between 20 and 40, between 40 and 70. We've explained what's happening in each section: constant speed, constant acceleration, constant speed, deceleration at a decreasing rate. And then we've given data and calculation to support each of our answers. Part 2 then. During the first 10 seconds, the bus travels 50 meters. Use this information to construct a distance time graph for the first 10 seconds only on the grid below. Distance time graph, this is a different kettle of fish. Our head's got to be in a bit of a different gear for this. Okay. So what we aim to do here, well, firstly, we've got to sort out our axes, which we should have, well, we should be going across in 2s for our time. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 there. I can't see very well on the laptop screen, so I'm going to guess to an extent where these are. 2, 4, 6, 8, 10, like that. And then our distance, well, we're going up to 50 meters, so we want to be going up in 10s for this to fit the graph. Again, I'm going to guess roughly where they are because I can't really count them on the laptop screen. 20, 30, 40, 50. And then we're going to have a point at 10:50, which is the data that we've been given. Okay, bus travels 50 meters in the first 10 seconds. And we know that from the previous graph, between 0 and 10 seconds, we have a constant speed. On a distance time graph, that looks like a straight line going up. And that should meet the point there. Obviously, you would do that with a ruler. Okay, so that's the graph there. And then use the equation distance equals speed times time to calculate the distance traveled by the bus between A and B on the graph opposite. Okay, between A and B, our speed was 20 meters per second. And the time period for which we were traveling was 20 seconds. So distance is speed times time. 20 times 20 is 400 meters. And we've used the equation that we've been given there, but we could also have worked this out by doing the area. Now this is a rectangle from A to B, the area underneath it. It's a rectangle with a height of 20 and a width of 20. How do you work out the area of a rectangle? Height times width, 20 times 20 is 400, which matches with our answer. And that is the end of the questions on distance, speed and acceleration. Now, there are some more questions in the booklet that deal with car safety or road safety rather, how we drive safely. But I will deal with those in a second video. Diolch bawb. I hope that this was helpful. Ta-da.